All right, so here in this lecture, we are going to study the logarithm functions right here. Okay, so it is strictly required that anyone arriving at this lesson here or lecture here must have already viewed or watched my other lecture, my video lecture about what the logarithm operation is. Okay, and so if you haven't done so, if you have not learned from in my style of teaching logarithm functions before getting to logarithm functions, I introduced what a logarithm operation is and how to calculate with logarithm. And so make sure that if in case you haven't learned what a logarithm exactly is, not a function, what a logarithm operation is. Okay, then find my lecture about what a logarithm is, or in other words, find my lecture on the introduction to the logarithm as an operation. Okay, so it's strictly required that anyone arriving here must have watched that other lecture of mine, where I introduced the logarithms. But then, other than that, knowing about all the properties of logarithms is before learning about logarithm functions is not really a must like that. So anyone learning logarithms with me, sometimes you can learn about logarithm functions before learning all the properties of a logarithm. Okay, or you can learn about all the properties of a logarithm before you learn about what a logarithm function is. Okay, so after getting some introduction to the logarithm as an operation, then learning the properties of logarithm before learning about logarithm functions, or learning about logarithm functions before learning the properties of logarithms, any one of that order, any one of those two orders is going to be fine. All right, but so now other than that, let's get to it. And needless to say, anyone learning in this lesson here must understand what a function in general is. Okay, and normally for a course in pre-calculus, then this material must be learned somewhere near the end of an academic term like that, where you have seen enough understanding regarding functions and seen other kind of or other classes of functions already. All right, and so now let's put the title away. So now, as far as the idea of function, now I have other lessons where I introduced other kinds of functions, but allow me to approach this, the teaching of this kind of function a little bit different. If you happen to come across my other lessons where I introduce other functions, then at some point in the earlier part of the lesson there, I will immediately give a formal introduction of what that function is. Okay, but now for logarithm, allow me to wait until somewhere near the later half of this lecture in order for me to come up with a formal definition. But then, believe me, we can start out with a few functions and you will already have in mind before a formal definition about what a logarithm function is. Okay, and so again, there's no need to come up with a formal definition of what a logarithm function is yet, because I want to wait until the right time for that good definition to come in. Okay, so now just to start out from scratch right here, allow me to just get in the idea with a demo problem right here. Or actually, it doesn't even have to be a demo problem. It's simply I'm going to promote a function. I'm going to define a function. And so in my expectation, you already know what a function is. So a function is simply just a rule. So now I'm going to define a function f of x as following. So now at this point, anyone knows that a function is a rule. It takes an input. Okay, and then we name the function f right here, and the input is indicated by this x variable. So now here's my function. I am going to define the function, and now after we have learned what a logarithm is, so now I'm going to take that operation that we're calculating logarithm, I'm going to define a function f of x to be log, how about log base 2 of x? All right, so simply now, in the way how I see the whole thing here is a rule. The rule tells me, according to what we have already understood well enough about what a function is, then this rule is indicating that for any value of x, the rule says we're going to take the logarithm base 2. We're going to apply log base 2 to that input x. And then whatever that comes out after the computation, after the calculation, it's going to be our output. That's how we should see this function at this point. So don't worry about what a logarithm function is. See, I don't need anyone to worry about what a logarithm function is. But right here, what you have is a function where the rule of this function applies a logarithm base 2 on our input. Okay, so simply just that, we have a function. We have a function. So now what can we do with this function? All right, so far, what else after defining this function can we do? And now back in my lecture where I introduced about what a logarithm operation is, then this is called a base, okay? And so it's just a brief reminder. So any base, the base I use here is a value. So here just something that we know for here, it's a positive value. So the base 2 is of course positive value, and the base 2 here we're using is clearly a value other than 1. So just a reminder, and here needless to say, as long as I decided that a base that I used, as long as I decided a base to use in my logarithm right here, that base must have already met all the requirements to be the base of a logarithm operation. Okay, and so this understanding came from our previous learning where I introduced about a logarithm. Okay, and then any base I'm using for any function later on that I define that involves a logarithm, then you know, needless to say, the base that I use there or that I used here must have already met all the requirements to be a base, the successful requirements for being the base. So here my base has to be a positive number and other than 1. Okay, and so now back to what I was saying, we want to keep digging in further into what can we do with a function that involves logarithm like this. Okay, or what can we do with a function that we define as, you know, taking the logarithm calculation, logarithm operation on a given input x. All right, so let's see what we can do. And so now allow me to get straight into this understanding, and then we're gonna start pointing out what we can do. But for this function right here, and now anytime it comes to studying about logarithm, it is extremely important that we mention about this. So as far as the inputs that we can provide for this function, because now any function has a characteristic that anyone must know that always comes along with a function, the domain of a function. The domain of a function, the set of possible inputs that a function can take. Okay, so here, in case that if you already learned from my the lecture where I introduced the properties of logarithms, then we have learned from that lecture that for any logarithm, in order to calculate the logarithm, the value I now as a function I call that the input, but simply looking at this problem as a logarithm operation, then this x right here is acting in place of the arguments of that operation right there. And so we've learned, and I'm saying if you have already learned from my properties of log lecture right here, then logarithm can only operate on those arguments being positive. That's straight into what I was trying to say right there. But now, as I said earlier in the beginning of the lecture, in case you have not seen my lecture, or in case I'm teaching about logarithm functions before I teach about the properties of logarithm. Okay, some quarter I mean in some academic term, depending on the situation, depending on how the academic term goes, I may start out teaching. I may end up with teaching about logarithm functions before teaching the properties of logs. Okay, and so in case you have not learned about the properties of logarithm, now I can just simply tell you right now that without seeing my other lecture, then anytime we're working with a log, we need to work with positive arguments only. And then the reason why it has to be the case here, we can wait until sometimes later in the particular lecture here, so that I can give the full explanation. And so I'm trying to go as independent as possible with that lecture, where if you've seen it, with that lecture about the properties of logarithm. I mentioned this in that lecture there, but in case you haven't learned that, that's okay. In this lecture, I will give an explanation for this as well. Okay, and so now that's one more requirement. That's one requirement. Anytime we're working with a function where a logarithm is involved. So specifically right here, how about just log base 2 for now? For this function, it can only take positive x value. Okay, only positive x values. Okay, so now I'm going to start doing a few calculating problem right there, and then we're going to find out the reason why a little bit. Okay, so now once we agree that this is a function, and this provides for us, right here, promotes the idea that we can only, the domain for our function, just right from this understanding, the domain for this particular function is anywhere between between 0 and positive infinity. That's another important understanding that we concluded from this requirements. Okay, but again later on, why do we require the arguments to be positive? It will get to a thorough explanation later part of this lecture, in case you have not seen how I lecture about the properties of logarithms. Okay, and so now upon defining this function, let's just simply evaluate a few values right here. Let's give the function here a few different inputs and get comfortable with working with this particular, the log base 2 of x function. All right, and so now just to keep this as a requirement, we only use a positive arguments. And now seeing this as a function, then I'm talking about we only use a positive input value. That's why I wrote it down as a domain here. So now to evaluate this function, I can start out trying f of x equals 1. F of x equals 1. All right, so f of x equals 1. So now seeing this as a function, then when x equals 1, the rule of this function says we take log base 2 of the input 1. That means we take log base 2 of 1. All right, and so now log base 2 of 1. We ask ourselves, now definitely you must have seen my introduction to a logarithm, and so with a problem like this, it's easy and simple enough to see that log base 2 of 1, what power of base 2 can equal 1? What power of base 2 to equal 1? And so algebraically, we are experienced enough in algebra that power 0 of base 2 equals 1. Power of 0 of base 2 equals 1. And so in that way, log base 2 of 1, the answer is 0. All right. And so that connects directly with our understanding after I introduced in my lecture where I introduced what a logarithm operation is. All right, so that's how we evaluate our function f of x, previously defined here as a log base 2 of x. Now f of 1 equals a log base 2 of 1, and that's the output here, 0. So this is output. This is now the argument. Now it's the argument of the log, but now it was the input of our function. All right, so let's give it a try again. All right, so f of 2. According to the rule previously defined here, I'm looking at taking log. The rule says take log base 2 of 2. And so the input is x equals 2. But now into this rule over here, then the input becomes the argument of our log function, of our log operation. Okay, so log base 2 of 2. Again, we have seen this enough throughout my introduction lecture on the logarithm operation. So we're asking ourselves that question. What power of base 2 that equals 2? What power of base 2 equals 2? Scratch work again. What power of base 2 to equal 2? That power there has to be 1. So, or in another way of saying, as an answer, power 1 of base 2, power 1 of base 2 equals 2. And so the answer to this is 1. All right, so now this number that I put in the box, it's output. It's output. This is input. Right here down, it's input. All right, and we can continue a few more different inputs right here. So far, I've tried x equals 1. I've tried x equals 2. My intention here is to generalize those positive values right there. Okay, and so now, this is just a little informal. But why is it that we cannot take a negative? I mean, why is it that only positive? Okay, so let's give it a try right there. And then I will come to a formal definition, a formal explanation of why we cannot take negative answer and why we cannot take 0. We only take positive values. We will get to that the explanation more thoroughly, but right now just give it some experiments right here. So particularly for this problem, for this function log base 2, okay, then let's say when input equals -1, for example, okay, f of -1, let's see what's happened. At least as far as the rule of the function. Now I see this as a function previously defined. F of x is log base 2 of x. So with this function, with the input being -1, we're looking at log base 2 of -1. Okay, we're trying to find out a little bit about why it's impossible to take negative inputs for this log base 2 function. Okay, we don't just blindly take hey, the requirement has to be inputs positive. So we want to get into the bad zone so that we find out why we shouldn't be there. Okay, so this is the same as saying, what power of base 2 what power of base 2 making this overall equals negative? Okay, in the world of taking exponents, especially when the base is already a positive number, no matter what value we try, no matter what value, what power we give for power 2, we always, and we're only going to end up with positive value. And so it's never possible to find an answer that meets that equals -1. And that is the reason why negative input here does not work. All right, but that's for this function. For right now, I only focus on log base 2 of x. So log base 2 was an operation, and now log base 2 of x as a function, as a rule to this current function f of x. And we have found out so far -1 substituted into the function didn't work out. I just gave that brief explanation here. Okay, and so now I'm saying that this is undefined. And so that is making it, again, consistent with the fact that requirements that I addressed here earlier. So earlier, as I was stating, in case you have not if you have already learned from the lecture where I addressed the properties of logarithm, then you will see all of that explanation there. Otherwise, if you have not seen that lecture of mine, or even if I have not taught that at all, if I have not even made that lecture at all, then just now take that as a requirement where I'm telling you right now. And then we experimented that on the other board right there, a little bit as an explanation. But that way how it is right now, everything I'm doing on the board is in regards to this log base 2 of x as a function. Okay? And so using this -1 input right here, generalize the idea that for any other negative inputs, this function will not take negative input. This function log base 2 will not take a negative input. So for -1 specifically, we have an output being undefined. So and for any other negative inputs, the output will also come out undefined. Okay, so what about 0? Let's experiment it again. Let's experiment it, and then later on I'm going to give I'm going to give a formal explanation, a complete thorough explanation within this lecture here of why we, in general, for any logarithm operation or any logarithm function, if we would define it, okay, or on any function where we have logarithm involved, then we only take positive input. So what about 0 here? according to the rule of this function, then it's going to become log base 2 of 0. Log base 2 of 0. Okay, and just right after you have already learned from my introduction video about what a logarithm is, it should be enough for you to start thinking a little outside of the box here. We're asking ourselves that question: what power of base 2 that can equal 0? What power of base 2 making this equal 0? But alongside with what I have explained earlier when I was going over this input -1 right here, anytime, well, provided that the base here is already a positive value and other than 1, then for any power of this base right here, we just will not get a value equal 0. We just won't. Is that 2 to the -1 power? 2 to the -1 power is indeed a positive 1/2. It's not going to equal 0. 2 to the -5 power, okay, is that going to be giving me a 0? It's going to be 1 over 32. It's not going to equal 0. Is that 2 to the 0? Okay, 2 to the 0 equals 1 in algebra. It's not going to equal 0. So in other words, it's impossible. It's another place where we cannot find a power making 2 raised to that power equals 0. So now, in other words, this logarithm that we're doing right here, this logarithm calculation, log base 2 specifically in this function, log base 2 of 0 gives me another undefined. We have an undefined output right here. Okay, and I don't think I need to write down the word output. It's an output being undefined when the input was a negative number. So I used -1 here, but I generalized that any negative input is not going to work. 0 here as the input also gives me an undefined. For this function, f of x equals, the rule says, log base 2 of x. All right. So these are a few, these are about a few cases of the critical things that we should avoid. And so now we know clearly that we have to set ourselves in that safe zone right here. For this function, anytime working with this function, we have to use an input being positive. We have to use an input being positive for x, or the domain here. Anywhere, if we pick a value anywhere between 0 and positive infinity, that will give us a defined output. But stepping outside of that zone, we have undefined output. All right, so let's continue. So we're still going to evaluate further. So now we know we just can't take x equals 0 for this function. We can't take a negative value for this function. But so then let's try now. It's not going to look pretty, I admit, but think about the line of number. 0 is here. We can't take that 0, leave it an empty hole here. And we cannot take any of the negative value here. I crossed it all out. So we can only take these values here. But think about 1 right here. We already had that from the other board. 1 is giving me an output being 0. But we can still try these values in between 0 and 1. And as I said, we already tried x equals 1 right here. And we had a successful output value. I wrote it down on the other board. Okay? But now, in this zone, we can pick any value as long as it's still greater than 0. It's still positive. It's still, so in this interval, right here, in this zone right here, it's still positive value. All right. So in that way, back to what I was saying, that it's not going to look, it's not going to look pretty in a sense that we have to, in that interval between 0 and 1, if we pick the value, then it has to be a fraction. How about here? Let's look at 1/2. Okay, let's look at 1/2. So now for our function here, the rule of this function f says we take log base 2 of the input 1/2. Okay, but that means we produce for ourselves a calculation very familiar that we've already learned from the lecture where I introduced the calculation with logarithm, the introduction about logarithm as an operation. Okay, so now log base 2 of 1/2. What power of base 2 that can equal 1/2? Okay, the answer for that, with just some experience in algebra and from our past understanding, or from our understanding from the past courses, then the answer here has to be -1. -1 power of 2. -1 power of base 2 equals 1/2. We have learned this from our previous courses in algebra. All right. And so now the answer to this. So now we have a defined output. This is output again. All right. And so just along that way, I'm going to continue to give a few other, not so pretty inputs. So how about f of 1/4? All right, f of 1/4. And so now that means this is going to be according to the rule of this function f. We take log base 2 of 1/4. All right, and that gives me now, so think about it again. 2, what power of base 2 that can equal 1/4? Okay. If you need some time, pause the video and think through. I see the answer, and we can still do this with mental math. Okay, I see the answer should be -2, because power -2 of a 2 equals 1/4. Okay, so now the answer to this, -2. And this is a defined output, a successful output. All right, and then how about f of 1/8? All right, f of 1/8. Then we have log base 2 of 1/8 according to the definition of our function right here. Okay, and so now I'm running a little short of space right here, but think about what power of 2 that can equal 1/8. That answer there must be -3. Okay, so now we have another output right here. As long as our input is given as a positive value, we will have a successful output. All right, and then I'm going to get back to my other board, erase out some work that I have left here for long. Okay, so we've had f of 1, f of 2. Okay, and I want to get some more into the larger value, whole value, instead of just instead of just fraction like on the other board. So we already had f of 1 equal to giving me 0, f of 2 giving me the output being 1. So now we can do, how about, and now with these values, we can go with f of 3. That gives me, of course, according to the rule of the function, log base 2 of 3. But a value like this, with an input being 3, the output value is not so easy to be determined with our mental math capability. So with something like this, we need to use a calculator. Okay, and so you must have also learned from my introduction to the logarithm that we don't have a direct button for this log base 2 right here. Okay, but we only have, according to our learning about the logarithm operation, we only have a button for natural log and the log base 10 right here. But we can still do the trick right here. So on a calculator, in order to calculate log base 2 of 3, then we can make a choice according to our learning, according to what we have already learned from the introduction to logarithm. Then we can make a choice to go with natural log. It's a choice. Natural log of 3, close the parentheses, and divide by natural log of 2. This 2 came from the base of our problem on the board. Okay, so log base 2 of 3. So I was doing natural log of 3 divided by natural log of 2 on my calculator. And so now I'm ready to hit enter. The answer has to come out in some approximates and in decimal. Quite a lengthy decimal over here. So 1.58496 and a lot longer. All right, so approximately, so when it gets to something like this, where it's beyond our mental math capability, then we have to use a calculator, and it has to be in some kind of approximate instead of exact value. So in 3 decimal places, which is normally what I use, 1.584, and actually in 3 decimals 585, and there's still a lot longer, but that's all we need right now. And we can go with f of 4. So f of 4 for this function, according to this definition, it means log base 2 of 4. And now with this one here, it's easy for our mental math capability. What power of 2 equals 4? What power of 2 that can equal 4? All right. And so now that power here has to be power 2. Okay, so now our output here is 2. So that's output, approximate of the actual output of log base 2 of 3. This is the output of log base 2 of 4. Okay, and then we can do another one. So how about f of 8? Okay, so 3 and 4, technically I can also do f of 5 like this, so that but we have to use the calculator. I can do f of 6, f of 7, but we all have to do those. We have to do those all on the calculator. F of 8 is something that our mental math skill can handle. Okay, because it's base 2. So it means we're looking at log base 2 of 8, and the answer here has to be 3, according to our experience. And allow me to start assuming that anyone learning from this lesson here has already been experienced enough with calculating the basic log, at least having some sense about how we can mentally calculate these logarithms right here. Okay, so that I can save our time to keep swinging back to these the ultimate questions to answer the logarithms. All right, so now I've sketched down a few values. And so far these, once again, the main idea about function. We've seen this long ago, since the beginning of our time learning together. Anytime we have a function, we're going to start having fun with throwing in different input values and then come out with output values. And that's what we have been doing. Okay, that's what we have been doing. So see, once you have a function defined right here, then the one big important work we can do to evaluate the function at various different inputs. All right, and so now that we're done looking at the some evaluated outputs, it's time to summarize all of our work into a table of values. We have inputs, we've got outputs. Okay, we've got inputs and we've got outputs. So let's put them all into a table of values. So, of course, I had to erase some of my work already, but hopefully anyone learning along with this lesson have already taken some notes there, so you can follow along easily right here. But so now putting all of the inputs and the outputs together as a table of values. This is again something very common to anyone working with a function, or this is a very common practice for anyone working with a function. And as a matter of fact, if we look back at any other functions that I've introduced throughout our time learning together, then this is the first time we're being introduced to a function where we let logarithms involved in a calculation like that. And so we're going to start think about if this is a brand new class of function that we're about to get in right there, then constructing a table of values will be a big stepping stone, so that later on it's going to lead us into sketching the graph, physically sketching the graph of this new function we just defined. All right, and so now for inputs, I've had, and then for y value here, yes, that's the function output, f of x. So for inputs, I went to as low as, the input as low as, and of course, again, we already agreed that the input has to only be positive, so I went to as low as 1/8 for the inputs, and I came out with -3 as the output. Okay, and that's still on my other side of the board right there. I have, when inputs being 1/8, f of 1/8, going through that calculation, give out -3 as the output. Okay, and then so that's just a brief reminder of those small or low values. Okay, but still positive. They're all positive values. See? The negative or the 0 inputs, they already gave undefined calculated value right there, or output. And so now, 1/2, I mean, numerically order these values right here into a certain increasing order from top down right there. Then 1/4 is the next larger value right there I used as the input among my evaluation problems. And so I ended up with the output being -2. Okay, so we just summarize what we did right there. And then when input was in 1/2, then we came out with the -1 as the output. All right, and then when input was 1, we came out with the output being 0. All right, and now I'm going to continue my table here. X is for the input, the output is y value, but that's the output of a function. We call that the y value. All right, so now when input goes higher than 1, I substituted in x equals 2 very early in this work right here, and I now already erased that. But when x equals 2, the function output was 1. Okay, and then when x equals 4, when input equals 4, okay, I no longer have that on the board here because I had to erase all of that. Then the output was 2, and then when input was 8, okay, then the output was 3. All right, so now we have a table of values lengthy enough to start getting somewhere. Now I also skipped out one value when input was 3 specifically. We came to that output being 1.585 and a lot longer. All right, we've had all of those input and output values like that. And believe me, you can go with f of 5, f of 6, f of 2.5. As long as the input is positive, we will get an output. But there's no need to place too many values in here, too many inputs right here. Just within these pairs of values will be enough for us to see some result in the next step right here. All right, so now you can start seeing my intention. I'm going to translate this, just like the idea of how we learn about function. So once we have a function defined, we're going to start having fun with evaluating the function at different inputs. And then we keep records. We keep recording those outputs and inputs, and now we put them all into a table. And that's why we call it, it's a table of values. Okay? And then after table of values, we're going to plot these pairs of values as coordinate points on the graphing plane right there. And then that shows us the graph of our function that we're currently working with. Okay? And that's the idea right there. So now I'm going to turn over to Desmos. Okay? So one more words before I switch to Desmos here, but again, I'm trying to copy that work where if any of us here is any of those early generation of mathematicians where they first explore about the function of this function log base 2 of x right here, then my graphing space that I'm about to show here is to be in place, is a substitution for the actual graphing paper. And so we think about, we're going to put those pairs of values from the table of values here as plotted points on the graph right there. And then we're going to plot and then physically draw the picture through. Okay, so that's the idea right there. So right now, even though I'm using technology, it's not intended to show you how to use technology. Okay, to get the graph here, it's just I'm using the technology here to describe that if we were doing that with papers and pencil, that's how we do it. Okay, so with the table of values you have already seen, then now on my graphing space, all of those values, the entire table of values are represented by these plotted points right here. All right, so now we can quickly double check here. For example, this point is when x equals 4. I'm going to show the label over here, the coordinates label over here, 4, 2. That agrees with what we've had in the table of values. 4 for x, 2 for y value, 4, 2. Okay, and then let's continue. And now for the next point, if we're looking at this point, for example, 8, 3, okay, and then we have here, now for this graph here, I even use, I overused my Desmos a little bit. I even got into the 16, 4 right here, okay, and you can easily verify, anyone viewing this lesson here can easily verify this. when the input x equals 16, we have output equals 4. And now on this point right here, it was on our table values 2, 1. And now for this one here, 1, 0. Okay? And so it looks like this point right here, once we draw the graph through the points here, through the plotted points here, then it's going to be our x-intercept right there. Okay? Something to keep in mind right there. And then now I have another point right here. See, 0.5 is the same as 1/2. So 1/2 comma -1. Exactly, this is exactly reflecting what's on our table values. And I have this point here right there at 0.25, which is a quarter, 1/4 comma -2. And here I have right there 1/8. 0.125 is the same as 1/8. So 1/8 comma -3. All right, and so now just looking at the plotted points for now, and especially in a far zoom level, right there, in an extremely far zoom level, then we already have a good feeling about what the shape of this overall graph is going to look like. It's a trace through these points right here. All right, so now back to that zoom level that we were at earlier. And so now I'm going to go ahead and use a paper and think about if we were on paper and pencil with a pencil, then I can just simply now sketch through. Okay, I'm gonna just simply draw through those points right there. It doesn't have to be straight line connect between those adjacent points, but it's already appear to be a curved shape and a rising curve right there. All right, so now we're gonna just try our best to draw a curve through those points right there. That's all it takes. All right, so now on the graph itself. All right. So go to the right first, go to the left first. It's all our choice like that. But see, now this is all right. So now I'm going to draw. See, now I start seeing. You can see that they're starting to have some motion right there. All right. So if I use a hand sketch, I will draw that piece, and then I'm going to continue drawing through those other points. And now that completes my graph. Okay, and of course it looks like it stops here, but simply because, you know, once we already had a good picture of the graph, it's just indicating that it will continue to grow further out. All right, and so now that's our graph for this is the graph of log base 2 of x. That's the graph of log base 2 of x right there. All right, so let's put the graph back again and have some further look to understand how the graph appears to be consistent with all the details I've written up here, aside from these table values, aside from the 2 table values here, because we already, from the table values here, we already translated those into the plotted points. So there's no need to check for consistency with the table values here, but there are other details here. Let's check for that. For example, I stated it clearly before we even got into evaluating these inputs here. Evaluating the function at these inputs, that we can only take positive inputs for this function defined here. Okay, or consequently we can say that this function has the domain being anywhere between 0 and positive infinity. Okay, is that so? All right, so now back on my graph right there. All right, back on my graph, and you can see that. Okay, at any zooming level of my graph right here, then you can see that the graph stays strictly to the right hand side of the y-axis. The y-axis is here. The graph in red color stays completely to the right hand side. Okay, so now when I'm saying the graph stays completely to the right hand side, some of you viewers, some of you students viewing this lesson may doubt what I'm saying, because you see a part where it looks like the graph comes together with the y-axis. But as a matter of fact, now with Desmos, it's powerful enough that I can scroll the mouse button, the mouse scrolling wheel, and now that's zooming in. And as I keep zooming in, see, at a certain area where we see and we think that it's overlapping, the graph overlaps with the y-axis. But now zooming it in, we're going to start seeing some difference. And then it's still indicating that the graph in red stays to the right hand side of our y-axis right here. All right. And so now that proves what I just said earlier, that the graph in red stays completely to the right-hand side of the y-axis. But in other words, it means that x values, see the portion of the graph still being visible right here, the portion of the graph stays, like I said, completely to the right-hand side of the graph. Completely to the right-hand side of the graph. It means the x values can only be positive, because positive is where we place the x values to the right-hand side of the y-axis. Okay, so the graph stays completely to the right-hand side of the y-axis, so indicating that x is the inputs for the graph. It's positive. Okay, and that confirms that, we have our function here strictly on the domain anywhere just between 0 and positive infinity. Okay, 0 and positive infinity, or we're only taking inputs being positive. All right, so that's some understanding for us right here, and we already saw how the graph appears to be very consistent with the information we already traced down right here. So this property came out from some of the brief explanation before I got into the graph, and then the graph reflected whatever is here and appears to be very consistent with what we have found here. Okay, all right, so now that's the end of the story. That's the end of the story for this function that I call log base 2 of x. I still did not give a formal definition of what a logarithm function is. This specific function is only defined as, hey, the rule says we take log base 2 of x for any input x to the function. That's all I'm showing at this point. Okay, that's all I'm showing at this point right here. All right, and so a little further into the graph, before our journey gets too far over here, a little further into the graph, just this graph specifically, we can see that, as I said earlier, connecting together with the fact I said earlier that this graph stays completely to the right-hand side. Okay, we already knew that. But now further, if we think about this graph right here, think about the direction of where the graph is heading, then as we keep getting closer, as the graph gets closer to the y-axis here on the right-hand side, because clearly there's nothing on the left-hand side of the y-axis, but then this graph gets closer to the y-axis, gets closer but will never cross. Okay, gets closer but will never cross. So, and my technology here has a weakness, so it kind of stops right here, the way that I set up the simulation here, but it's technically keep extending down further as the x value get closer to the line, to the vertical y-axis. So, in other words, my point in another characteristic I want to point out right from this graph, right in this graph, that this graph is recognized to have a vertical asymptote. Okay, so let's draw down some notes right here. All right, and then so some further understanding about this graph right there. So what we recognized here is that all right, so what we recognized here is that this graph, the graph that we're seeing here, okay, clearly it agrees with what the graph shows a domain being anywhere between 0 and positive infinity. We already knew this even before we pulled up the graph. But the graph now shows that something that we did not see this through on the board before getting the graph. We have a vertical asymptote. Allow me to call that VA. Vertical asymptote, okay? We have a vertical asymptote at x equals 0 for this graph, for this function. Okay, so this is what we recognized about our function f of x defined as log base 2 of x. Okay, and this VA is a name that is short for vertical asymptotes. Okay, vertical asymptote. And so that's one characteristic. This is the second characteristic. And right now, looking right at the graph right here, another characteristic that I want to point out is that the graph has an x-intercept right at 0, I mean 1, 0, 1, 0. So this right here is our x-intercept. Okay. So we have as another characteristic right here, we have x-intercept, okay, at 1 for x, 0 for y. 3 characteristics that we recognize right out from the graph for this specific function. F of x equals log base 2 of x. Okay, so this is now really the end of the story for this particular function. F of x equals log base 2 of x. All right. So now think about what if I define a function using logarithm, but using a logarithm operation, but with other base? Because right now I focus on base 2. Okay. Right now, right here in this function that I promoted the idea, I used base 2. But so what about other than base 2? And so now recall from our introduction to logarithm, where logarithm there was treated simply as a mathematical operation. Then aside from base 2, we have base e, we got base pi, as long as the base, and I also emphasized it here, I reminded that here, as long as the base is a positive value and being other than 1. Okay, then so other than base 2, what do we have here? So think about when it's other than base 2, then we can define a function f of x to be log base 3, okay, of x. That is going to be a completely fine looking function. What I mean is it's entirely fine to have to define a log base 3 of x, simply because the base here is a positive value and other than 1. We have that. Okay, so what about can we define a function where the rule says we take log base 0.5 of an input x? Sure, why not? As long as the base here is a positive number and positive, we can define a function where the rule says take log base 0.5 of the input x. All right, and then we can also now recall that the e is a new constant that we've learned recall from our understanding from the exponential functions like that. Then the e is a base where at 2.718 it's a new constant aside from the pi like that. Pi is a known constant that we've known for a long time. Okay, but the e is known in a more modern math like that. Okay, so we can define the function here f of x as log base e of x, because e being 2.718, approximately 2.718 is a value that's positive and other than 1. Okay, allow me to go a little informal here. Positive and other than 1. That's why it's entirely legal to write to define a function where the rule states that we take log base e of an input x. Okay, and then recall from our lecture, from our learning about the introduction to logarithm, then we don't write log base e like this, but indeed we actually write ln. That's the formal symbol for log base e of x. So yes, we can define a function where the rule says take log base e, or natural log. This is how we call that. Take natural log of x. And for anyone who has some serious intention to move on to calculus after pre-calculus here, then pay good attention to this function, because this will be the logarithm. This will be the function that you work with very often in your calculus course. Okay. But any one of these functions so far, the rule says we take some kind of logarithm. This is a log base 3. We take a log base 0.5. This is a log base e. So any one of these functions, the rule says takes a logarithm. A logarithm, I mean in respect to a given base. Okay, take a logarithm of our input. All right, so what about another one? We can define f of x equals a log base 10 of x. Sure, why not? As long as the base is a positive value and other than 1. Clearly, it is the case here. All right, and so log base 10 of x is going to be just fine to be defined as a function. So now this rule says, this rule is stating that we take log base 10 of our input x. Okay. All right, but then again, recall from our lecture on the introduction to logarithm operations, then we don't write log base 10. Internationally, we write log. We skip the base anytime it comes to base 10 of a logarithm. So the formal symbol now that's accepted worldwide is just log of x. Okay. All right. So these are just a few examples of functions that involve other logs. And I'm not saying that these are all we have. There are a lot more as long as we can come up with a number being a positive number and other than 1. That number can be a base. And then from there we can define a rule that taking log in respect to that base, that given base of the inputs. And there we have a function. Okay, and there we have a function. All right. And so now, ladies and gentlemen, all right, so now it's still not a formal definition of what it is yet, but any one of these functions right here, including the one we've had earlier, where I already erased, f of x equals log base 2 of x. Okay, so any one of these that I list here, yes, we call them. Any one of these is a. Okay, any one of these is a logarithm. Okay, function. All right, this is a logarithm function. This one here, where my arrow points to, is a logarithm function. This one right here is a logarithm function. This one right here is a logarithm function. Natural log of x is a logarithm function. All right, and the one we defined and worked with previously is a logarithm function. So now you're starting to have a hang of what a logarithm function is in general, but still, this is not a formal definition of what a logarithm function generally is. I still want to save that for much later until you have learned and become mature enough in your understanding. Then that good definition will come out later. Okay, so right now here, you see simply the function is a rule, and anytime our rule is stating that we use a logarithm to calculate based on with the input, we call it as a logarithm function. Let's keep it that simple for now. And again, I keep stating that we are not at the formal definition of what a logarithm function is yet. All right, but now with that limited and basic understanding, it's enough to drive into a lot of problems for us to work through, okay, and to experiment. All right, so now I'm going to take you into example 1 where we're going to learn to sketch a logarithm function. So now I can formally use the term logarithm function, but still I avoid giving out that formal definition. So any one of something like this or anything else similar, basic enough, okay, then we're going to call it as a logarithm function. So in this example 1 that I'm about to show here on the board, let's try to learn to sketch so that we can repeat the steps. You have seen already how I've done that with log base 2 of x. You've seen how I sketched the graph for this. So let's specifically try that again, okay, so that we can formalize the step to get yourself comfortable in case the technologies fail and you still can draw your own graph like that. Okay, sketch your own graph. And then so stay as closely with the log base 2 that you have seen earlier. Okay? All right. So now for this, let's call that example 1. All right. And in example 1, let's sketch Okay, let's sketch the graph of. All right, so how about problem A right here? Yes, among the list of those logarithm functions that I've had here, and these are just a few of them. There are a lot more out there, okay? But among the list that I have here on my board right here, let's sketch the graph of this function, log base 3 of x. Log base 3 of x. All right, so yes, the example, the worded instruction of the example just made that call. We're going to sketch the graph of f of x equals log base 3 of x. So now we're going to recall from the steps where I introduced with the log base 2 of x. We're going to follow the exact same steps. But really, here I'm just going to get straight into, because on standard, that's how it works. Anytime we're about to sketch the graph of a completely brand new function, think about it, we're having this function here as the first time ever, okay, even without seeing log base 2 of x earlier, okay, then how would we get the graph of something like this? Yes, we have to evaluate values, okay, we have to evaluate values and then put all of those recorded values on a table of values. That's the idea, okay. And so good thing we already had some experience with the log base 2 of x we worked with earlier. So let's investigate a couple of things. Is it still true that for this function we should only take is it still true that for this function we should only take positive inputs? Okay, is it still true? Because this was brought up when I was investigating about the log base 2. So let's see if it's the same for log base 3. It's a different function already, different rule. And now I'm talking about, I'm showing to those who may have not seen my lecture where I introduced the properties of logarithms. And so that's why let's assume that anyone viewing that here is completely at scratch. Okay, and so let's see if it's still true that x, the input has to be positive. Okay, well, to answer that mystery, let's brutally give it a negative. Log base 3, see, f of negative 1. That equals log base 3 of negative 1. We're trying out to experiments for ourselves like that. Okay, that's equivalent to the question saying, what power of base 3 to make it all equal negative 1? All right, can we really find such power? No way. All right, so obviously negative inputs doesn't work. It gives me undefined. All right, so we're starting to be a little more convinced that x should be positive. Okay, at least now no negative. At least at this point, I tried negative 1, but it generalized for other negative inputs. We should not take a negative input. So as far as the inputs, it should be non-negative. All right, I ruled down that possibility of using negative inputs. No way. Okay. What about, again, what about when we tried exactly 0? Try and error, trial and error. Okay, that means according to this rule, we're going with log base 3 of 0. Okay, log base 3 of 0. Okay, think about that question again. Can we find a power of 3 that makes it equal 0? No way. It's not going to work. Okay. Negative power, like a negative 2 power, it gives me a 1/9 algebraically, but 1/9 is not equal to 0. Okay. And any other negative value, no matter how infinitely larger negative value we choose, it's still not going to equal 0. How about 3 to the 0 power? It's going to equal 1. It's not equal 0. Okay. And so now it's clearly no way. We can't find a power that, 3 raised to that power equals 0. We can't find that power. All right. So again, this is another undefined output value. All right. So now we are so firm that the input has to be completely positive for this function. For this function, I still have not made any generalizations about all of those log functions out there yet, because we still didn't even get to a formal definition. All right, So now, the reason I pointed this out, because now once we agree within ourselves right here, then now when we are about to construct a table of values, we must choose values where we have to satisfy the inputs being positive. So we narrow down the possibilities of picking the wrong inputs. Okay? Or actually, I said the wrong way. We ruled out the possibilities of taking the wrong inputs, and we narrow down all of our input set to just the positive only. That's the idea. Okay, so now x, let's sketch down a few values right here. Okay, and I may need to produce two separate tables to continue. All right, so how about we already agree that we cannot take 0 or negative, so I'm going to go with 1. All right, so calculation says, and you can, at this point right here, if you don't want to do mental math, you can use your calculator. You can use your calculator. 1 here means f of 1. Okay, f of 1 means log base 3 of 1. Okay, and once you have already viewed the lecture on the introduction to logarithm, you will know how to access the calculator even if no calculator has a direct button for log base 3, but you can still use your calculator for something like this. Okay, so the answer will come out for sure being 0. That's what log base 3 of 1 is. All right, and so we've had that value erased. We can try. Now allow me to use my own experience to lead the way a little bit. I'm going to indeed, the next value, instead of choosing 2, I'm going to go with 3 here. Okay, because it's making it easy for the mental math. So when x equals 3, we're looking at f of 3 to be log base 3 of 3. Okay, you can use the calculator similar to how I demonstrated that with the log base 2 function earlier. Okay, and assuming that you have already watched my introduction video on how we work with logarithm. Okay, so now, and I don't think I need a calculator for something like this. The answer is 1. Okay, we have an output here is 1. That's the output, that's the input. That's why I'm writing that in the y column right here. All right, and yes, you can try 2 right here, but there's no need for doing that. We can try, how about the next one here, and you can give the inputs being 5, 6, 4, 5, 6, 7, 8, or even 5.5, any inputs that you want as long as the inputs being positive. But now for my table of values, I'll purposely choose the next one after 3 here to be 9 for my x. Okay, so now when we get 9 for the inputs, then our function will look as following: f of 9, that equals log base 3 of 9, and log base 3 of 9 equals 2. Okay, you can use the calculator to verify this. All right, so I have outputs 2 on this. Okay, and again for another value, how about one more value? Allow me to skip all of those other values. I'm going to jump straight into 27. Why? Well, again, allow me to use my own experience to lead the way. In this example, I chose these values because they will eventually be easy for my mental math capability. That's all there is. Because these are easily recognized as a power of base 3. That's just my little secrets behind the scene. Okay, but if you go with the x equals 10, x equals 11 or 12, you have to use a calculator because it's beyond our mental math capability. All right, so f of 27 will equal log base 3 of 27. Okay, so now that's the function. The function says that the rule of the function says we take log base 3 of this input 27. We come out with the outputs being 3 this time. Okay, you can use your calculator to double check with my mental math capability, but I highly recommend any of my students who learn from this lesson to be able to still maintain your mental math capability. Okay, it's a gift that you have, that you can do mental math. Okay, now outside of these whole values, again, we don't want to go with negative, neither 0. We only want to stay with positive inputs. Okay, and so now in that way, we have no choice rather than going to something less than 1 but still positive. So how about 1 over 27? See, again, out of nowhere, why do I choose a value like that? And why not a 1/5 or why not a 1/2? Okay, because this can be, at least with some experience enough, you can see that this can be easily expressed as a power of 3. Okay, but you can use your calculator on that value as well. 1 over 27, when we substitute into the function 1 over 27, f of 1 over 27 equals log base 3, okay, of 1 over 27. That will give me an answer, the output here being -3 indeed. Okay, so -3 is the output here. All right, and then again, allow me to use my experience to introduce the next value. The next input here is 9. So these inputs are meant to be independent, but I chose them for some good purpose. All right, but really there's no rule about how to choose an input for any function. All right, and so now quickly calculating this, f of 1/9 equals a log base 3 of 1/9, and that will give me an output being -2. All right, -2 is here, and so I can go with another one. How about 1/3 right here? All right. And so f of 1/3 is the same as when it's f of 1/3, the rule says take the log base 3 of 1/3, and now that gives me -1. All right, -1. All right, I believe the table of values is long enough, even though it definitely did not cover all values right there, and we don't need to do that, just a few will be good enough for us to see the shape of the graph. All right, so now let's turn over to Desmos here. So we got the first step down, table of values down, and now the next step is to take this table of values and put them on the graphing space. So if I'm using Desmos to represent a piece of graphing paper, a piece of graphing space with nice grids and all that, that's all, with precise grids and all that. Okay, but we're going to translate all of these pairs of values into plotted points. Okay, and so now, all right, so now my graphing space is here, and so now anyone viewing the lesson can pretend that this is a piece of blank graphing paper, or a blank piece of graphing paper over here. And so, all right, so here, this is my plotted points right from the table of values that we've had. All right, so I put all of those pair of values, all of those pairs of values on the graphing plane like this. So, and let's check for consistency right here. So that point right here is right at 9,2, which agrees with our value here, 9,2. Okay. Now the graph didn't show 27,3 because the zooming did not allow that. So let me change the zooming a little bit. All right, so I'm going to zoom it out a little further, okay, and drag it all the way out here. All right, but the 26 is the most I can go for now. All right, so 27 is here. All right, so again, this was 9,2, 27,3 is here, all agreeing with the table values so far. And then that point is 3,1. This point here, 1,0. Okay, so these points all agreeing with the table values. And then we have this point right here being 0.333, -1. So 0.333 is the decimals, the expression of 1/3. So this is, in other words, 1/3, -1. Again, another point that agrees with the table values. And then this is the next point right here, 0.111. This is really 1/9, -2. So 1/9, -2. And the last point I have on for my table values in this point right here, it's at, see, this is 1 over 27. Desmos gives it, my graphing utility I'm using here is expressing that as a 0.037. And it's supposedly 0.0366 and a lot longer, but now it's well, in fraction is 1 over 27, -3. So we have all of these points. All right, so now let's put in the graph. All right, so now with the graph, allow me to show the graph as following. So I'm going to use a piece of pencil and imagine together with me that if we draw, it's going to look like that. All right, and then that's one piece, and then we're going to continue from this point and draw straight over to the other piece right there. All right, so that's how the graphs look. Okay. So now that's the graph for this function. Now we have the graph for our function right here. Right here that I'm seeing the function for, we've sketched the graph for log base 3 of x. Okay, allow me to quickly erase out this table of values because we already have seen all of those on the graphing space earlier as plotted points. So now, because we want to again recognize, even though the question only says sketch, but that loose term right there has a lot of work involved for us. First thing, get the table of values and then put the table of values as plotted points on the plane, and then we're going to sketch through. Okay, and now even though it was not asked specifically here, let's take this opportunity to recognize some further feature from the graph of this function log base 3 of x so that we can start forming into some generalization right here. Okay, but then later on when we get to part B, then I don't have to do this. So first off, the shape of this graph is very similar to the one we've seen in the earlier function, log base 2 of x. Okay, so now just observation right here, or I say recognize. We recognized, just take note on what we recognize right there. Okay, the shape is very similar, okay, to the graph, okay, of f of x equals log base 2 of x. That's one of it. Okay, and again, allow me to still keep the graph here in the corner of the screen right there. Right, the shape is very, see, it's that shape right there. Okay, very similar to the one that we had earlier for log base 2 of x. And now, for the domain of this, once again, does the graph appear to be consistent with this requirement, inputs being positive only? Yes, look right in the picture. The graph stays completely to the right-hand side of the y-axis. Okay, so yes, the domain is once again anywhere between 0 and positive infinity. Okay, so what about vertical asymptote? Does it appear to have vertical asymptote? Okay, so now in full screen view, y-axis is here. Seems like the graph is attempting to get closer and get closer and get closer to the y-axis, but it will never cross. All right, and so that's how I'm seeing it. So now I can, as an estimate from looking at the graph here, as an estimate from looking at the graph, then I can see that we have, yes, we have a VA, right? We have one unique VA. So allow me to push this bullet a little bit further out right here. So VA, okay, we have a vertical asymptote. That's what VA is for, vertical asymptote at x equals 0. This is really the y-axis. That's what it is. Okay, so these are all very similar to that graph of log base 2 of x. That graph of that function log base 2 of x. All right, so at least now that's just for now enough for about this graph right here. Let's look into part B of our example. So this time I won't have to show all of these details anymore. It's just anyone learning in this lesson already got a good hang of that. Okay. All right, so now part B of the example, we entirely just treat this part B as a problem where we want to just provide a sketch. So we start out with table values again and put those pairs of values as plotted points on the graphing space and then make a sketch through like that. That's all. So part B, the function given here is f of x equals, now the rule is saying that we take log base 0.5 of x. All right, log base 0.5 of x. So just again as a quick flashback right here, but among these were, among these functions that I brought up, where I already called that any one of these is a logarithm function right here. I'm going to investigate, I'm going to explore the graph of that particular function. It's now a function. It's just simply we already learned that we can take logarithm operation on any value right there. So we take that as a rule. So now I'm going to define a function where the rule is stating that we take logarithm base 0.5 of an input right there. Okay. All right, so in that way, again, let's start out with sketching the table of values. And this time I really am going to pick up the pace right here, because you have learned all of that techniques right there. And at any point, if your mental math capability is not as fast as how I go up here, then you can always pause the video to double check with the calculator. Okay, so now I'm going to start out with the table of values. Okay, and then I'll go with, and again, I suggest these values. Allow me to use my own experience to suggest these values. So I'll go with 1. Okay, and then there's 2. Okay, and then I'll go with 4 for x, and I'll go with 8 for y. I mean for x as well. Okay. And then I'll go with the inputs being 1/2. Okay, I'll go with the inputs being 1/4, and I'll go with another inputs being 1/8 like that. Okay, and you can also double check with me at this point right here that the input should be positive. Right now, I suggest this, but you can use a calculator and to quickly try out with a negative value and a 0 value for this function, and experiments for yourself like that. That we only take positive inputs, and that's why my table of values here only list down positive inputs. All right, and so now when x equals 1, we come out with an output 0. When x equals 2. When x equals 2, we come out with output being -1. Okay, this is f of when x equals 2, it's f of 2. That is log of 0.5, log base 0.5 of, and by the way, base 0.5 is a 1/2. So log base 1/2 of 2. Okay, and that answer there is a -1. Okay, and so now when x equals 4, we should come out with an output being -2, and now that gives me a -3 for output when x equals 8. You can always pause the video and double check on any of this. Okay, on any of these. All right, and then when x equals 1/2, okay, f of 1/2 is the same as taking log base 0.5 or log base 1/2 of 1/2. All right, and then the output should be 1. All right, so this is 1, and then we're looking at this 1/4 right here. The input should be positive. The output should be 2. 1/4 is the input. The output now should be 2. When the input is 1/8, the output is going to be +3. All right, so +3. So for the output, so that should be enough for our table of values. All right, and again, feel free to pause the video anytime you need, okay, to use a calculator and verify any of my calculation here. All right, but now it's time to turn over, after you have already verified all of my calculations here, let's turn over to the graphing utility and pretend that graphing space with my Desmos graphing utility there is a blank piece of graphing paper with nice and precise axes and all that, and with grids and all that. Okay. All right. So once again, this is my empty graphing space right here. All right. And so These are now the plotted points. All right, these are the plotted points right here. Okay, so let's check for consistence. So these point, that very low point right here, that lowest point on the right here is 8, -3. Just exactly consistent with the table of values that we've had right there. Okay, and this point is 4, -2, another point right out from our table of values. This point right here reflects 2, -1. Okay, and this point right here is the pair of values 1 for x, 0 for y. And this point right here is for the pair of value 1/2 for x for the input and 1 for y. This pair of value, this point right here reflects the pair of value 1/4 for x and 2 for y. And this one right here I have here is 0.125 for x, means it's 1/8 for x and 3 for the output right there. All right, so now that we've had all pairs of values are plotted here on the graphing space, now it's time to just bring in the graph, to sketch the graph. All right, so now I'm going to sketch it out. Okay, I'm going to just try my best to draw a nice curve to follow through these points right there. All right, and I'm going to sketch the other way, okay, to reach through all of those other points. That is our graph for, this is now our graph for log base 2, okay. This is log base 0.5 of x. That is the graph for log base of 0.5 of x. All right, so again, just a few quick things to check for consistency, but the graph still appears to be on the right hand side of the y-axis, as you can still see on the screen right there, making it consistent with this. We got vertical asymptotes and all that. I don't have to write it down, but we have vertical asymptotes right at the y-axis right there. Okay, and it still has that that x-intercept right at 1, 0. All right, so all of these properties we've seen, but the shape here now is different with the earlier graphs. All right, so we will get into that even more formally. All right, so now in this example here, we're done with part B right here. Now allow me to put in one problem for you to try on your own as an FYT. All right, so now as an FYT, you can try the following one. And this one here, I'm not going to show my own steps anymore. Once I write it down, you can feel free to pause the video to follow through your own steps like that. Okay, but how about I want you to graph the function f of x equals log base 4 of x right here. All right, so get your own table of values and then put the table of values on the plotted points as plotted points on a graph, on a blank piece of graphing paper, and then sketch the graph through like that. All right. And so now, assuming you have already spent some time working on the graph, and pause the video. Okay, so now I can go ahead and show the graph. All right, so on my graphing space here with Desmos, and if you were doing this on your own calculation, then we can go with the following points right here to make it easy, to make it simple for us. Okay, so these are my plotted points, but if I would do it myself, I would use 16 for the inputs, another value 4 for the inputs, those values that stay as much as possible on the grid right here, and 1 for input. But then these are a little hard to choose, so you could have chosen 1/4 as well. But other than that, you have your own values. But these are, if I was doing it, those are my values right there. Okay, and this point at the bottom here is the same as 1/64. Okay, and this point right here is the 1/16, (-2). All right, but now after all of these points right here, now here's the sketch. That's the sketch of my function log base 4 of x. Log base 4 of x is here. All right, so now we are ready for another example. And in this example, the intention is to introduce how you can use a technology to graph, to sketch the graph, to generate the graph of to get the graph of a logarithm function, any of those logarithm function that we have seen earlier. Okay, and at this point, even though I start using that term, a logarithm function, but keep it simple, it's just limited within those we have seen so far. Okay, there's a logarithm. It's a function that's defined as taking the log to a given base in respect to a given base of a value of an input value right there. Okay, but then the aim for this example 2 here is to use a technology. So I'm gonna focus on Desmos right there. And then I will also have another part where in the lecture here where I show how to use a standard graphing calculator with a TI 83 or 84 calculator to get the graph. But then other than those two technologies right there, then you are, anyone learning from the lesson, if you are using a calculator different from those, from the graphing calculator or the graphing utility I'm using here, then make sure you read the instruction manual of how you can generate the graph of any of those, any of these functions I'm introducing. Okay, so now this is example 2 right here. So now I'm going to say how about we're going to use a technology. Okay, use a technology to graph. Okay. All right, and that's all we need. So what are we graphing here? Let's say part A of this example. So let's look at f of x equals, so now it's my function here, and the rule of this function is taking the logarithm base e, so natural log of x. All right, natural log of x. So this is log base e, and it was, this function was among the list of some of the quick logarithmic functions that I erased just now. Okay, so this is log base e of x. Okay, log base e of x. But simply at this point right here, since we have not had a formal definition of what a logarithm function is, then just simply think of this function here as a rule. Okay, and this rule here is stating that we're taking the log base e. So log at this point in our understanding is simply a mathematical operation. So we take the logarithm base e operation on every input x. That's how we understand about this function at this point right here. All right, so now I'm going to first start out with using Desmos right here. I'm going to show how we can use a technology. So Desmos is my first one, my priority one right here. And so for anyone who plans to use Desmos with me right here, then Desmos can be found at the website www.desmos.com. Okay, so that's the Desmos, and then after the quick demonstration, the quick illustration with using Desmos, I'm going to swing over to using in the same problem right here. I'm going to show how to get the graph of this function using your TI calculator, graphing calculator, a TI 83 or 84. Okay. All right, so now on my computer screen, once you have come to that website, www.desmos.com, then this is the main screen right here, and all we have to do is click on that button that says graphing calculator. All right, and so this now, it will bring you into the very familiar interface where I've been using that for most of my graphical illustrations throughout the other lectures that you have seen. All right, and then this button right here, with that button we can adjust a couple settings. So now I'm going to adjust the jumping step on each of my axes here to be in a scale of 1, in each step of 1 right here. I don't like these minor grids, so I'm going to turn those away. Okay, I'm going to turn those off. I want to use the arrow that's pointing one way. So now my axis is here, half arrow, and I want to turn it into the bold phase mode right here. Okay, so the line weights appears to be a little heavier now. All right, so this is an empty space right here, ready for action. So the command entry line is on the left hand side panel right here. So right here, I'm going to go ahead and click in that empty space right there. So to graph the function natural log of x with Desmos, then I'm going to type, and there are two ways of doing that, but I highly recommend doing the formal way by typing out the formal functional notation. So here f of x, f in parentheses x. don't worry about any of these fancy things that pops out here. Let's continue our command where the blinking cursor is at. So now I'm going to say equal, okay, and then the natural log is simply just ln, okay, ln, and then Desmos is smart enough to recognize that it's a natural log. It's the natural log function. It's the command for the natural log function. And now this is a good thing to understand right here. It's not only just Desmos, but it's for any technology, any graphing utility, any graphing technology, and any calculator. Anytime that we're working with log, it's best to use parentheses. So now I'm going to open parentheses. And then now my input is x. Now I just type it. And now immediately you already notice that the graph popped out. So that's how easy and how quickly we can use the graphing utility with Desmos here to get our graph. Okay, so I was saying that typing out the function name this way is the formal way, because now you can also hide away the graph by simply clicking on that icon, and that hides away the graph. Okay, and then with Desmos here, you must have seen that in some of my other illustrations throughout other lectures already, but I can be more than willing to show that again quickly here. But we can click on another empty space where the mouse cursor turns into a finger pointing right here. Click into the space next to that, and it pops out another command entry line ready for entering a different function. So we can graph multiple graphs in one graphing space here. So just now I hid away that graph for natural log of x. Okay, and so back to what I was saying earlier. Even if we skip the f of x symbol as above right here and only type natural log of x, Desmos is still smart enough to know that, hey, this is the function that Desmos is supposed to graph. So in a situation where you don't have too much time, then you can just type in just the function itself, and it will still give you the graph. But doing it this way right here, so if you simply just type in natural log of x, Desmos will know the graph. But for the next step, if you need to do a calculation, if you need to do an evaluation problem, for example, f of 1, Desmos will not understand what f is all about. That's why this symbol right here is basically the way that Desmos is asking you to give a definition of what f is. Okay, and so that's the reason why I want you to stick with the formal definition. That's typing out f of x equal natural log of x. This is so now once we have typed that command right here, then Desmos will automatically, that for any other command entry after this command entry line right here, Desmos will take the definition of f of x as natural log of x. So now f of 1 is the same, is quickly evaluated to be 0 here for any of us. Okay, and so I show this the command right here, this feature with Desmos, so that you can use Desmos not only as a tool for graphing, but also as a tool for quickly getting plotting points like that. Okay, so now, but that's really not what we need at the moment here. So let's close that. We can clear that out. That's deleted completely. So now let's put the graph back right here. All right, so now this is the graph for Desmos. This is the graph for Desmos. And that is how easy and how simple we can use the graphing utility with Desmos to get the graph for our function natural log of x. And so it's right now this function here is I call this function here a logarithmic function right here, but simply because it was one among those I brought it in earlier right there. Okay, we looked at in that list I erased earlier. There's a log base 2, log base 3, log base e, log base 10. So for those I had on the board earlier, I call them the logarithmic function. So this was one of them. All right. So now on the same function here, let's turn over to the graphing calculator with the TI 83 or 84 calculator to see how that calculator there can help us handle the graph, or getting the graph quickly or instantly getting the graph of this function. Okay, so we're still in part A of the example. All right, so now we're on the graphing calculator with the TI 84 the calculator. So just for anyone to be aware, but TI 83 and 84 works similarly. So it's just this version of mine. This version of my TI 84 has a little bit of a nicer print of the mathematical So the graph will look a little nicer in terms of better resolution, and the math prints or the superscripts and powers will look better than the older calculators, that's all. Okay, but the functionality will be exactly the same. And so now to graph the function f of x equals natural log of x, I'm going to go ahead and click on that button y equal right here. All right. And then you must have seen this once or twice in other video lectures of mine. So the calculator is strong enough to graph multiple functions for us in one graphing space right here. And so now with this particular calculator, I can graph up to 9 different functions. But for some of the older calculators, maybe 6 or 7. Okay, and then this particular software that I'm using, this particular version that I'm using, can even put color on multiple graphs like this. So making it clear which function is which for us. Okay, but that feature here is not important. TI-83 users will not see this, but that should not change the way how we get the graph of our function. So now our function is natural log of x. So now I'm going to go ln, click on that button, and now automatically the calculator generated that parentheses. So again, that's just the way how any machine. So Desmos was using it. Now the TI calculator, the TI graphing calculator is doing the same. It puts your inputs of the function inside the parentheses. It's a good habit so that later on, if we work with machines, it's a good habit to bring that into machine and make machine work correctly. All right. So now back to the calculator. Then the x input is not the usual alphabetical x. So it's not this letter x right here on my screen. Okay. The x input as a variable is found right here in this key, and you must have seen my explanation here a couple times in other video lectures already, but here I can just explain that again. Okay, so that's the x input right here, and so now close the parentheses. So that's how simple it is to type to input our function natural log of x into the calculator. All right, and simply hit enter, and now after hitting enter, that function has been stored. And now our blinking cursor on the calculator is at a different functions line right here, ready for entering another function. But we're not going to do that. So here we only stick with one function. So it looks like I chose to put, it was just my choice. I put my function natural log of x in the blue color right here. All right, so that's something to expect. Later on when we see the graph, our graph for this function will be in blue. Okay, you could have, anyone learning in this lesson could have also input your natural log of x under y2 right here, making your graph look red later on. Okay, but that's pretty much all of your choices right there. All right, so now that once we've done inputting the function, we're going to go ahead and click on the graph button, and now we get the graph. Okay, now we get the graph. And so now when we're on a calculator, when we're on a graphing calculator, we don't have as much flexibility as when we're in the graphing utility with Desmos. And so now if you want to change the viewing window over here, there are a couple options. You can change the window by setting a maximum or minimum on the x-axis, setting a maximum and a minimum on the y-axis. That's how we can change it. It's not as simple as just grabbing like Desmos. I can just simply grab the graphing space and move it so that I can change to a different window. But here we have to really go to each button right here and change the window, but it shouldn't take too long. And then we can also zoom by clicking on that zoom button. Zooming out is gonna, as it says right here, we're gonna zoom out the graph so that we can have a more complete view of the graph. Okay, and if this is the center of the zoom, and clicking on that, it's gonna give me a zoom version. And now if I want to zoom in, I'm gonna click on zoom, but select zoom in. Okay, and now if I want to change that to this point, for example, okay, use the right arrow key, and okay, so on the calculator will not understand the mouse cursor unless we use the mouse cursor to press on the buttons. But think about if we're operating with the calculator completely by fingertips right here, then we have to press on all of these buttons. So now this is about where I want to put in the zoom as the center of the zoom. So now I'm going to click enter. And now the zoom is popped in and it's centered this part of the graph. And we can see a little more detail of the graph. All right. And so it's not as simple as how we do that with Desmos, but it's still, it's still a working solution for us to get the graph using a technology, to get the graph of our function here, natural log of x, f of x equals natural log of x, to get the graph using a graphing device, a graphing technology. All right, so now that's all for this part A right here. We put our function in the TI 83 or 84 calculator. We got the graph of our function using Desmos. So now I'm going to start picking up pace a little bit without much explanations. Let's graph against a different function, okay, using a technology, because there's still some more details I want to mention. So in the same example over here, I am going to graph, and we want to use a technology, and I'm still going to stick with both graphing technologies, the graphing utility with Desmos and the graphing calculator with the TI 83 and 84 calculator. All right, so how about our function now is f of x equals, let's say, in my lecture note, I prepare log base 2 of x. All right, log base 2 of x. So I introduce this function as an introduction to logarithmic function right here. And then we've seen how we have already seen how we sketch the graph by hand on this particular function, log base 2 of x. Okay, and so now we're going to learn how to instantly get the graph of something like this using technology right there. Okay, so this time we're going to learn how to completely let technology handle the graph for us, but we still need to learn how to navigate around to make technology get the correct graph for us. The main problem is that, as I have explained, a general log like this, a log base 2 or a log with a base other than e or base 10 is not available immediately in a lot of graphing technologies out there, especially those standard graphing calculators on the market, the TI 83, 84, the TI Inspire, all of the HP graphing calculators, and including all the Casio graphing calculators. None of those has a button for log base 2. None of those has a button for log base 5 or something like that. So none of those has a button for log other than base E and base 10. Okay, so let's see how we can get around with that. So first, again, I'm going to show how we can get this with Desmos right here. Desmos is a little bit more flexible. It's actually quite more flexible. But I don't intend to promote Desmos or anything like that. Okay, so once I'm done with the lesson, basically it's options for you as technological options for you to get your graph done in many situations where you need a quick graph to decide to make a decision for your assignments or anything like that. Okay. So now I'm back with Desmos right here, and this is the current graph from the previous problem of part A, and I still want to keep this one here. So this was from part A. I just want to show that with Desmos we can enter multiple graphs at a time. Okay. So now how about this next function here on the board? I call it f of x because I wanted to treat it as a different problem. But for Desmos we already since we kept f of x here, since we keep f of x here as defined as natural log of x, so we have to give a different name, okay, for the log base 2 of x. So we can call that g of x, and we just type out the command as usual. We just type out the syntax as usual, g in parentheses x, and now hit equal. So log base 2, now there are two options of doing this. The easiest option to understand is to click on that little button at the bottom of your web browser right there. Once you're in Desmos, click on that button at the end right here. It will pop out all the syntax. So now these are all the basic math prints right here. You can click on functions, okay, and now we turn over to. So we click on function, click on miscellaneous, okay, and the short form of that is MISC right here, and click on that button right here that says log base A. So this is to indicate a general log right here, other than, see, this is log base 10, and that's log base E, and right here is a log base A right here. We'll get the log base, the general log base A templates ready for us. So now you can see that the mouse cursor, the blinking cursor is in the in the subscript mode right here. So now I type 2 in here, okay, and now I'm going to click on there, or we can just use the right arrow key. Now once we're in subscript mode right here, we can just use the right arrow key on our keypad. Okay, and then that gets out. We can see that it gets out of a subscript mode, and we one more time hitting the right arrow key, we are now inside the parentheses. Now type X. All right, and now I can hide away this typing panel, and now I close the parentheses. This graph right here in purple is now our graph for log base 2 of x, and that's how simple it is. So, and just now, so there we go. Just now, Desmos is showing the graph for two functions. F of x is from the previous problem, part A, natural log of x, and now in purple, this graph right here is log base 2 of x. If we for Desmos right here, specifically for Desmos, if we want to change the color for any of the graph right here, we can just point to that icon right here, click and hold for a couple seconds. All right, and then until a popped out menu, until a menu popped out like this, and so we can change the color. So right now there's a check on that purple color because the graph is being printed in purple color. If you would like to change to a different color, say blue, then now click on that blue, and then it's changed the color of our graph like that. All right, and then just click anywhere outside, and that menu is gone away. It's hidden away. All right, and now if you would like to hide away the graph of the preceding problem, of the previous problem, just click on that and to hide the problem. Okay, so now the icon is grayed out like that. All right, so that's how we can get the graph base, the graph of log base 2 of x on our calculator here. Now, in case as a different option right here. So now I'm just highlighting that command with the Desmos, and let's delete it out. So in case you, or for anyone who doesn't want to use, the typing panel over here, you can still type log, okay? And right now, without a subscript to indicate the base, then Desmos will automatically understand this as log base 10. But now to get to subscript completely using your keypad right there, you're completely using your keyboard, you can type underscore. So underscore will bring that down to subscript mode, and now we just type 2, and now again right arrow key, that brings us to we'll make it exit the subscript mode like that, and now we have parentheses, okay, and close parentheses with x inside, and now once again the graph comes back like that. So doing that, we don't need to open up that typing panel with Desmos, this built-in typing panel. So that's just more option for anyone learning about Desmos like that. All right, so that's how we get the graph for Desmos, for log base 2 of x using Desmos. So now with this same function, let's see how we can do that with the TI calculator, with the TI 83 or 84 graphing calculator. So now back on my calculator, this is the graph from the previous problem like that. This was a natural log of x, okay, and we can still keep it here. Let me return to the zoom level that was the default zoom level over here. Okay, so I'm gonna get back to zoom standard, okay, by clicking 6 after opening the zoom menu. So now we're in that original zoom level over here. All right, and notice that for any graphing any of the TI 83 or 84 graphing calculator, the default zoom is not in square scale over here. So if you would like to see square scale, see this is a 1, but the scale of 1 on the y-axis is a little bit shorter than the scale of 1 on the x-axis. You can see that. Okay, so if anyone on the TI calculator, if you would like to change the scale here to exactly 1:1 ratio, then we go zoom, and then we select that option that says z square. That's for zoom square. Okay, so that's option number 5, or we can just scroll down on the list to option 5 like that. Hit enter. All right, so now it's completely in square zoom like that. All right, but that's just about adjusting some setting. So now if we want to get the function log base 2 of x, now for a standard graphing calculator like this, it's going to be a little tricky right here. So we go y equal, just as usual. I'm going to use the down arrow key to point down to the next, because I still want to keep this function in blue. So now I'm arriving at a color being red. So this is where I decided to put my function in here. You can decide differently. But now to type log base 2 of x, we have two options. One option is, so recall from when we were learning, recall from when we were learning about the general introduction to logarithm, then any one of these calculators does not come with a button for log base 2. So we have to do a trick, a workaround right here. So we can go with choice number 1, we can go with log base 10, log. So now I can go log base 10 of x. But log base 10 of x is log base 10 of x. It's not log base 2 of x. We want log base 2 of x. So now we chose log base 10 of x. But make sure we divide that by log base 10 again, with log base 10 of 2. All right, so this 2 here comes out from the base. That 2 comes out from the base of our log right there. Okay, so recall from our introduction lecture that so now log base 2 of x, okay, can be done as, see, log base 10 of x over log base 10 of 2. Okay, so that's what you saw. I typed in my TI calculator, but this is just one among the two options here, just one option. So you can similarly do ln as a different base, ln of x, okay, and divided by ln of 2. Okay, and so we have seen this action back in the video lecture where I introduced about the logarithms right there. All right. And so now at this point we are ready for getting the graph of this. Just simply hit enter to have the calculator store this log base 2 of x. And so you can go you can also go ln of x divided by ln of 2. That will get you the graph for ln of log base 2 of x. All right, so now and remind yourself that you put or remind yourself where you put your own function, which color that you chose for your function right there. So I chose my function here to be in red color. All right, so now let's click on graph. All right, so the graph in red right now is the graph for our function log base 2 of x. All right, log base 2 of x. And that's how we're getting it. And then again, you can roll back, you can rewind a video to the earlier example, part A right there, to see how I can change the zoom setting and all that, and to navigate around, to have a better view with your graph right here. All right, so just now I demonstrated how you can get the graph quite instantly using some kind of technology. So I used a lot of Desmos. I rely a lot on Desmos to do the graphical illustration. That's why I feel it's useful that I can provide, I can share this tool, this graphing utility with any of my students who would like to learn right there. And besides, Desmos is also free, and it has really good graphing feature with it that comes with it. Okay, but also I showed how to use your standard graphing calculator that's widely used throughout many classrooms in the nation right there. Okay, so now we've learned a technology. There's some way to get the technology, provide the graph for us. All right, so now let's head on to the next understanding. So now that's the whole point of learning about technologies, because this is now the right place to let technologies instantly come up with many graphs of the logarithm function, so that we can start exploring more properties of more understanding, not just only properties, but more understanding about the graphs of a logarithm function. Okay, and so far at this point, I start using start hearing me using the term logarithm function a lot more often now. Okay, so basically at this point, it's still not a formal definition yet. Okay, but it looks like so far for all of the logarithm functions I've been using, it's a function where the rule of the function says we take the log. Okay, we take the log operation in respect to a given base right here of the inputs. So far any of those logarithm functions that we've been looking at, that's in this form right here. And yes, I will get into a formal definition to define what it really means and truly means to be a logarithm function. There are still a lot more than those of meeting our eyes right now. Okay, so yes, we're gonna investigate quite a few different logarithm functions, but of course for this, at this point of our learning, there's no point of making you sketch by hand, making anyone sketching by hand for every log function, because now once we have a definition, let f of x be log base a of x. And this definition, I mean, once we have defined a function being a logarithm function right here, then think about it. A log base 2 of x that we have seen quite a lot in actions, and a log base 10 of x, and a log base 2 of x, I mean a log base e of x, natural log of x. Yes, they have one similarity, they are log functions. But in the end, they're different functions, different rules. This rule is taking log base 2 of x of every input. This rule takes log base 10 of every input. This rule is stating that we take natural log of every input. Any one of them is different from the other ones. So this is more like a family of functions so far, and depending on what base we provide, what base in our logarithm, it will become a different function. So the function still becomes different. That's what I meant right there, depending on the base. All right, so that's the reason why now if I simply switch from a base 2 to a base 3, back in the ancient time where the mathematicians learned these functions from scratch here, then yes, they had to do it by hand. Okay, but now thankfully we have technology. So let technology handle so many graphs instantly so that we can, the faster we can achieve these graphs here, the better we can learn some good generality about the graphs of these different functions, but they're all being the log functions for now. All right, so let's get to it. So at this point right here, using whatever technology is pretty much your choice. Allow me to use Desmos throughout my lecture right here to do the demonstration and to have a visual illustration. Okay. And so now I'm just starting out. In the next activity we're about to head into, I'm just going to simply start out with some logarithm with a little bit of an unclear base, which is some general base, log base a of x. And I didn't even provide a specific base yet, because that's what we're about to do. We want to specifically investigate the graph. We have already seen the graph of log base 2. So log base 2 of x, this is where a equals 2 right here. Log base 2 is in that family, base 2, and we already seen that it had an intercept at 1, 0, and the shape is kind of like this. Of course, forgive me that I'm a little upscale right here, but the shape is a rising shape from the left to the right. It has a vertical asymptote. Okay? All of that details, hopefully I don't have to recall too much. Okay, vertical asymptote at x equals 0, the y-axis being the vertical asymptote, and it's completely stayed to the right-hand side of the y-axis. But all of those details right there were just from log base 2 of x. So what about log base 3, log base pi, log base 10, log base 0.5? What's going to happen? And that's the whole idea. That's what we want to get into. All right, so now we're on my web browser right here, and with Desmos already open. So on my left-hand side panel right here, I have prepared a good comprehensive list. And this is, when I'm saying comprehensive, I didn't mean to say that it has all logarithm functions out there, but it's long enough. But this list is long enough to illustrate my idea right here. So my list starts out with some of those logs where the bases are high value, a lot higher than base 1. And of course, we don't work with base 1 for logarithm. So, but these are all the values of the base greater than 1, and then it went from base 10 and base 5, base 4, base 3, and so on. And now after base 2 right here, I'm going to investigate those logarithm where the base is less than 1 but still positive. The base of a logarithm function has to be positive and other than 1. And that's why after base 2 right here, and I don't even want to bother with base 1.5 or anything like that, even though technically you could, okay, you can still work with a log base of 1.5, but there's no point of doing that, okay? And then after that, I switch to, and after base 2 right here, I switch to base log base 0.75, 0.5, and etc. and etc. So that's what I meant by a comprehensive list. It showed enough the different cases out there. All right, so now we already learned about log base 2 of x quite a few times. So let's show the graph of log base 2 of x one more time like that. All right, it's right here. It's that graph in red. And see, for fast purpose, I did not even bother typing the symbol f of x equals log base 10, g of x equals log base 5, because with a list of so many functions like this, we're eventually going to run out. I'm eventually going to run out of letters to name all of these different functions, and that's why I just go with a fast typing way. You know, log base 2 of x. Desmos will understand that it's a function. Give it a graph, okay? And then log base 10 of x. Desmos will understand it's a function. Give it a graph, okay? So just now we have log base 2 of x. So now I'm going to think about, and you can see that I put these logs in from the top down right here. I arranged these in a decreasing order of the bases. So base 10 is here, base 5, base 4, base 3. This is base 2.718, base e. Base e is clearly less than base 3, but still above base 2 right there. All right, so now starting out with log base 2 of x, we have already seen the graph here. So let's look at the graph here one more time. This graph, log base 2 of x, is completely to the right-hand side, of the y-axis. Once again, I already had that explanation for this specific function, because the domain for this function is anywhere between 0 and positive infinity. That's why the graph here appeared to be completely to the right-hand side of the y-axis. And this is also something we already looked at. This graph, log base 2 of x, has the x-intercept right at 1, 0. Okay, and now the shape here is the shape where it's rising steadily from the left to the right. It has fast, sharp rising, but as it passes through the x-intercept, the rising becomes more slowly and more slowly. Okay, so that's what we recognize about the graph of log base 2 of x. So now let's quickly, and let's still leave this log base 2 of x here, but let's put in the graph of the other logs so that we can realize how the different bases change the shape of another logarithm function. So now I'm going to show the graph for log base e, and it's in blue that just now popped out. All right, so as far as the graph right here, as far as the shape of the graph in blue here looks exactly the same, or at least very closely similar to the graph in red. So some difference here is probably just due to scaling and all that. All right, but as far as the shape, I see it's the same exact shape because it's still rising, rapidly rising before the intercept, and then rising, only slowly rising after it passes through that x-intercept like that. But it's rising one way from the left to the right. And right now with these two functions right here, log base 2 or log base e, these are all with base greater than 1. The base here is greater than 1. So the graph is pointing to the right-hand side, rising from the left to the right. Okay, and with the two graphs being on the screen right now, with the two graphs being shown right now, they all have that common x-intercept, 1, 0. All right, so far with the two graphs, we all discover that they both went through that x-intercept at 1, 0. All right, so that's it, and they both have a vertical asymptote at being the y-axis right here. I can put in some extreme zoom in level over here for anyone viewing the lesson here to see that the function in blue is also asymptotic, okay, to the y-axis, right at the y-axis. It's the blue curve. Let me hide away the red curve right here, but the blue curve, natural log of x, is getting closer to the y-axis. See the arrows indicating we're still looking at the y-axis. And now if I zoom in even closer, then we're still going to see some difference, indicating that the graph in blue is still to the right-hand side, but a lot closer to the y-axis right here. All right. And that's how I can say that this graph here is also, the graph of natural log of x is also asymptotic at the y-axis, or has a vertical asymptote being the y-axis right there. All right, and so now let's put the log base 2 back. So now let's change to a higher base right here. Let's look at a higher base, and I'm still going to keep these two graphs here, the log base 2 and the log base e. Let's put in log base 3. All right, so log base 3 now is printed out in green color. So log base 3 is still the same shape. Okay, now I'm hiding away the blue and the red curve right here. Log base 3 of x in green right here is still the same shape. Okay, it's just the part to the right hand side of the intersection point right here, of the intercept point right here, is rising even more slowly. So if I put back the earlier graphs, the graph base 2 and the graph base e here, then the graph base 3 right now is the lowest compared to these two other guys right there. Okay, the green graph here is the lowest when it's where it's to the right hand side of the x-intercept. But now for to the left of the x-intercept, then the green version is actually the highest one compared to the other ones. Okay, but in the end, it's still that primary shape that it's rising one way from the left to the right. Okay, it's rising one way from the left to the right. This graph in green also has the x-intercept, one x-intercept at 1, 0. It has a vertical asymptote, and the only vertical asymptote is at the y-axis right here. Okay, and it's rising one way. So now putting it together with the other graphs, we see that all three graphs go through that common x-intercept. Okay, and has the exact same kind of shape like that. Okay, so higher base makes the rising slowly and more slowly to the right hand side. That's what it is. That seems like that's what it is to me. Okay, and so now we can now keep putting in more logarithm functions of higher base right here. So log base 4, see the version in orange is now here. Okay, it's still that shape. Now I'm hiding away these other graphs. See, it's still that shape right there, very similar to the other logs that we brought up. Okay, and once again it has that x-intercept right at 1, 0. It has an asymptote, a vertical asymptote right at the y-axis. All right. And now with the graph of log base 5. Log base 5 come out in purple color. And this is the graph right there. This is the graph. All right. So now with 5 different logarithms function, and where I arrange them in increasing order, increasing bases from the bottom up right here, then you can see that as the base gets higher, then the graph itself bent down even more. So log base 5, okay, log base 5 still here, it still has that shape rising one way from the left to the right. Okay, it's still going through that common x-intercept at 1, 0. The purple graph still has a vertical asymptote right at the y-axis right here. But the shape keeps getting lower, the curve itself keeps being bent lower and lower as we change to higher base and as we change to higher base. And so now in that prediction, now before I put up the graph, before I turn on the graph for log base 10 right here, then anyone can expect that the graph here has to go through this point. The graph has to go through this point as a rising shape again. So now let me hide away these. Okay, or maybe let me still keep the purple version. So the graph for log base 10 that I'm about to show right now has to go through that point, has this y-axis as vertical asymptote, but being more bent down below this purple. And then this part right here has to be, closer to the y-axis and being above this purple one. So now let's have a look at that. Now in black. That's just exactly as what I predicted. Okay, but it still has that exact same shape right there, rising one way from the left to the right. And it seems like the turn becomes more trivial and more trivial at this area. Whereas now way back at log base 2, the turn was a little hard to see right there. Okay, it's just a nice round curve around here. But now when we get to log base 10, and it becomes a lot more like an angle. But it's still a turn. It's still a smooth turn. It's still a round turn right there. But it's a lot more rapid turn compared to this turn right here. All right, but still, all logarithms so far that we investigated, all of these go through that point at 1, 0. All right, so after investigating 6 of those logarithm functions, where the base, so generally speaking, I focus on those where the base is a value greater than 1. So of course it's positive. So now in that case that I brought up so far, when a is greater than 1, okay, what have we seen generally? So at this point, when I completely leave the machines out, right, then all it caught my attention about the graph is that the graph has a y-intercept at 1, 0. No doubt about that. We've seen it all through 6 examples right there, and we should be clear. And the graph now, in my mind, it's already stayed quite permanent in my mind. The shape of the graph, after looking at 6 different examples, the shape of the graph is like this, okay, a rising shape, making a turn, and then go through that x-intercept. And so how sharp that turn is, it all depends on how high that a is. So as a gets higher, as base gets higher than the sharp, the turn becomes more sharply and more sharply. That's all. And it's asymptotic to the y-axis. So the y-axis is here, the x-axis is here. That's what we have. And all of these graphs, I could have also mentioned that there, but all of those graphs stays any one of those graphs stays to the right-hand side of the y-axis. So now we can formalize all of that idea right here. As far as the domain of the graph of any of these functions, the domain for any of these functions, when base is greater than 1, the domain is anywhere between 0 and positive infinity. The graph stays completely to the right-hand side. It gets closer, it keeps getting closer to the y-axis, but it will never even hit. That's why the 0 side right here on this interval is an open interval. The 0 side is an open parentheses. All right, now we have x-intercept, okay, at 1, 0. This is for all graphs right here, for all graphs that we've seen so far. Log base 10, log base 5, log base 4, log base 2, log base e, log base 3. These are all having that shape and all going through that common point right there, 1, 0. So we call it as the x-intercept at 1, 0. Okay, and then the third feature that we observed right there, they all came out having vertical asymptote, a VA right here for vertical asymptote. Okay, any of one of those has a vertical asymptote. All right, at the line x equals 0. So it's a vertical line. And this line here can be understood as the y-axis. All right. So these are the 3 major characteristics that we observed from looking at these graphs with the base being greater than 1. All right. So I'm not going to erase what's on this board here. Let's get back with Desmos here and find out, so what's going to happen when the base turns into less than 1. Okay, so we want to head out for the case where base is less than 1. But of course, the base is required to be positive. All right, so let's look at the shape of the graph, okay, and then see if it's going to in any way change any of these observations that we've made right there. So let's now turn over to Desmos. All right, so now with my Desmos graphing utility, so now I'm still going to retain log base 2 of x right here. But now I'm going to put together with log base 2 of x, log base 0.75. So log base 0.75 is going the opposite way. So now instead of a rising curve, like the red curve here, log base 0.75 is a falling curve, falling from the left to the right. But it's still going to go through that point. It looks like the graph in blue here is still going to go through that same x-intercept where log base 2 of x went through. All right, so this curve in blue right here is the graph for log base 0.75. Okay, and it's a falling graph. It's still asymptotic to the y-axis, and the graph in blue still stays completely to the right-hand side of the y-axis. Okay, indicating that the domain for this function is also anywhere between 0 and positive infinity. Okay, so now let's look at another one. What about log base 0.5? All right, and now allow me to hide away the log base 0.75 right there. So now the graph is green. This is log base 0.5 of x. With this graph in green, again, with the log base 2 still being retained up here, the green graph is still going through that same x-intercept on the x-axis. It's still similar with the log base 0.75 in the sense that it's still a falling shape, falling from the left to the right and continuously falling. Okay, it's still going through that point. All right, and now, but not only a falling now, the log base 0.5 being a lower value for the base right here, being lower value for the base, the turn becomes more rapidly. Okay, so it was a rapid fall and then it suddenly turned and it's more rapidly turned into a slow fall. Okay, this one right here, rapid fall, but it turned into a slow fall much more slowly. All right. And so now let's look at log base 0.25. And log base 0.25 now is in orange. It still goes through that point, that x-intercept. Okay, it's still in that shape like any of those earlier with base less than 1 right here, falling from the left to the right. Okay, being asymptotic to the y-axis and going through that x-intercept at 1, 0. All right, and so again completely to the right hand side of the y-axis. And now let's quickly look at log base 0.2. So log base 0.2 is the purple one. All right, and it's the turn is even more rapid, making the graph here stays closer to the x-axis. Okay, where the orange one is still here and it's lower than the purple simply because the decimal value here is still higher than this decimal. All right, and so now this is log base 0.1, still falling from the left to the right. All of these graphs stay completely to the right hand side of the y-axis and being asymptotic to the y-axis. They're all going through that common point being 1, 0. All right, and so now we're ready to nail down all of those generalizations. So when the base a is less than 1 but still positive, of course, then the graph of our logarithm function looks as following. It's a falling graph. It's a falling graph. Okay, I can close my eyes and just draw that because I've seen that enough. That point here, that intersection point, is still at 1, 0. So we don't have to change this information. Okay, so it doesn't matter if it's, so now at this point, one generalization doesn't matter if it's base greater than 1 or base less than 1. The graph is still going to have an x-intercept right at 1, 0. Okay, so that's the one. But now the shape here changes from, see, that's why I have to draw the shape. Here, when the base is greater than 1, the shape is rising from the left to the right. Here, the shape is falling from the left to the right. But it's still going to have a VA, a vertical asymptote at the y-axis. So y-axis is here, the x-axis is here. Okay, and the graph here is still going to have a domain. It's still going to display a domain of our function being, well, the graph itself still stays completely to the right-hand side of the y-axis. So that's consistent with the domain still remains the same between 0 and positive infinity. So those three major characteristics exist in any of these logarithmic functions right there. All right, so that's some generalizations we can see about the graph of different logarithmic functions right here in that form where it's a log base a with a general base a right there of x. Okay, the kind of function where the rule of the function says, hey, take logarithm base to a given base, okay, of the input. All right, so now at this point, anyone watching the lesson here is ready for another example. Okay. All right, so let's now look at our example 3 right here. After we have seen and had some good generalizations about the graph of any logarithm function, the basic one right here. So let's look at example 3 right here. We just want to match, okay? We want to match each function with its graph. All right, so that's the worded instruction of the problem right there. Okay, so now the idea is I'm gonna provide a list of what I so-called logarithmic functions. Okay, and then we're gonna the point now is that, and then after giving the list here, I'm gonna give the 5 graphs right there, but they're gonna be shuffled the order all over, and they are gonna be colored differently. So we are gonna look at the shape of the graph to match that with whichever the function being given listed on the board here. So my graph, my function A right here is f of x equals the natural log of x. My function B is f of x equals log base 3.5 of x. My function C right here is f of x equals log base 6 of x. Okay, and these are not the ones that we've seen earlier through the Desmos demonstration. Okay, and now the graph, the function D here on my list is, how about f of x equals log base 0.85 of x. Okay, and then we have another one on my list here. My function E, f of x equals log base 0.35, okay, of x. So we have 5 functions here. Okay, so with these 5 functions here, of course, they're in whatever order they are. Okay, now I'm going to show the graphs of 6 of these functions, but they're all going to be shuffled with different colors all over. We're going to match them. Which one is it? The blue graph is being the graph for this, or is it the red graph being the graph for this? And then what color is the graph for any one of these? That's what we're about to do. All right. All right. So just now, what I have here with my graphing space, the graph for those 5 different functions that we've had on the board earlier. And so the point of the problem now is that the graphs come with different colors, but I'm going to hide away, or I hid away all of the grids, and so that we have no idea about scaling. Okay, and then we don't see the function, which function typed out this one, and that's what we have to do right there. We got to match which one here, which function among our list on the board earlier is the graph for red, which function is the graph for black right here. Okay, so we have to rely on the generalization that we have had here, okay, to make the estimate, to make the quick prediction about which graph can be matched with one of those functions I've had here on my list. Okay, so we have back on the graph right here. Allow me to show the graph in the corner of my page right there. So there's a red color, there's a blue color, there's a green, there's a purple, and there's a black right there. Okay, so I'm also going to use a different marker color right here to indicate. All right, but now this small screen right here is maybe making it a little hard to read right there. So I'm going to again swing back to the full screen view. But so we can see that there are, among these lists right here, some bases are greater than 1, like say base 6, base 3.5, and this base E right there, they are greater than 1. So in that way, before I swing to the graph, right here you can see that when the base is greater than 1, the shape has to be a rising shape from the left to the right. And the graph will stay completely to the right-hand side of the y-axis. But you see the case on my list earlier, when it's log base E, it has to be this case. Log base 3.5, it has to be this case right here. Log base 6, it has to be this case right here. So the graph has to be in the shape of rising from the left to the right. Rising from the left to the right. All right, so in that case right here, now if we're looking a little more closely into our graphs, so with the graphs here, then clearly those 3 graphs in red, in blue, and in green, they have to be, these have to be the ones for, these have to be the ones for these bases right here. But I still have not been able to decide who is who. But these three graphs right here are among the red, the blue, and the green right there. All right, and so we're starting to have some clue to trace down right there. Okay, so we have learned earlier. We have learned earlier that according to Desmos' demonstration we have seen earlier, now we know that when the base is greater than 1, right, then the graph is pointing this way, and they all have that common point, so that common point is not helpful much for us. But here's the thing. As the base gets higher, we've learned earlier, in the case where the base is greater than 1, as the base gets higher, then the graph turns more rapidly, and then become lower and lower on this side right here. All right, so with that clue right there that we have observed earlier, now we can decide. Okay. So now I see that this base is the highest base. I mean, out of these logarithms where base is greater than 1 right here, then this base here is the largest base for all three so far. And this is the middle large, and this is the least one out of the three cases. So that means if we're putting up the picture right here, then whichever one that bends the most and being closer to the x-axis after the bends. Of course, these are all rising from the left to the right, okay? But whichever bends the most will be the one that's with the highest base among these guys right here. That's the key. And then among these three bases, the one that bends least, that has the least bend right here, it has to be this one, because base E is smaller than base 3.5 and base 3.5 is smaller than the base 6 right there. Okay, so that's the information that we can trace it down. So now one more time I want to swing over to the graphing screen right there. All right, so on the graph here, it looks like among the graphs that's showing rising from the left to the right, then the green is the one that's most bent and bends down closest to the x-axis right here. And that's what I meant right there. Okay, this one in green. Now I put that in a little bit heavier weight right there so anyone can see it. All right, and then the blue is also bent. It's bent lower than the graph, but it's still above the green right here. So blue has to be the middle level, you know, somewhere in the mid level. Okay, between 6 and the other one. So I'm now very likely that this graph in green here has to be in for base 6 right there. And then this one here in red has to be for base E, and this one right here has to be for base 3.5. That's how we recognize. And so now I can get back on my board right here. And clearly, and I'm going to use I'm going to use color marker to start making that indication. So this is the lowest graph. This is the graph that bends the most and bends to the point that it stays closest to the x-axis, and it stays in green. And you can see that on the screen right there, it stays in green. So this one right here is the green graph. Now I recognize it. That's the green graph right there. All right, and then now I'm done with the green color. We nailed that down. And so now these two, one of them is blue and the other one is red, right? And so between the blue and the red that you're still seeing right here, then the blue stays more bends down compared to the red right there, because it looks like the base here is base 3.5, higher than that base being E right here, 2.718. And so now this one here has to be the blue version. All right, so I'm indicating that here. This is the blue graph right there. That's how I recognize it. All right, and so now, of course, among all the graphs there, the blue, the green, and the red, there are all those that matching with, that should be consistent with the base being greater than 1. So this is the remaining one for among those that rising from the left to the right. So the graph here has to be that red graph. All right, that's how I recognize it. And so now, all of a sudden on our list, 5 functions. We already nailed down 3 of them. Okay, so now with these 2 remaining logarithm functions right here, their bases are less than 1. So on this board of mine where I wrote it down earlier, so anytime that the base is less than 1, the shape is pointing this way. So it makes perfect sense with the observation that See, these two graphs, the purple one is pointing down and the black one is pointing down as well. All right, so these two have to be for those log base 0.85 and log base 0.35. But which one or who is who? Okay, which one is the black and which one is the purple? All right, so in our observation that we have learned earlier, then the higher, so they are less than 1, but the closer it is to 1. So let's say 0.85 as the base, 0.85 as the base, or 0.35 as the base. The closer the base to 1, the more flat now it is, and the further the base, okay, the further the base from 1, okay, the further the base from 1, because the base will never be equal 1, but now 0.35 is further away from 1, okay. So 0.85 is closer to 1. So the closer to 1 the base is, the more flat out right there, the more drop down it is. But then the further it is, the less close to 1 right there, like a 0.35 right here, then it's more going to be more bent and it stays closer to the x-axis. Okay, so whoever that stays further away with these bases less than 1, whoever stays closer is more flat down, stays away from the x-axis, but here it stays closer because the bend is more sharp. It has a sharper bend right here. Okay, and so now in that way, clearly the black color is more with a sharp turn, and this one here is with a very wide open turn right there. Okay, but these are all falling down graph, and so now with my markers available with me here, then I can note now that this graph in purple, okay, the purple graph that we had on the computer, on the graph earlier, is the graph for 0.85, and the graph in black, this graph in black is the graph for log base of 0.35 of x. All right, so that's how we match, and mainly we just rely directly on the shape of the graph. Okay, the shape of the graph, the direction of the graph, where the graph is going, and how bent the graph is. All right, so one more time, let's just look at the graph, the graphs of all these 5 functions to confirm our understanding. All right, so the graph in black right here is more bent because the base is less than 1 and further away from 1. Whereas the graph in purple right here is the graph where it's pointing down. Okay, so now in a zoomed out version, see, it's still the same shape right here, but it's a lot more flat out, flattened out right there, because the base, admittedly, less than 1, but closer to 1 compared to this graph in black. And now needless to explain again about these other graphs right there. All right.